graphics. He's got a lot of international and a lot of domestic experience.
For that. And then I'd like to thank everyone else who actually took the time to show up. So hopefully you're going to learn a thing or two about copper. And if you don't, well, at least you get to see some pretty pictures. So all the pictures you'll see in the slides today are pictures that I've taken from fieldwork on the Colorado Plateau over the years. So the plan today is to talk about sediment-hosted copper, and more specifically, to talk about red beds and why you should not be using the term red beds at all. Okay, so here's the plan. The plan is this talk has 3 parts. The first part is talking about red beds, and I'm talking about red beds so you never talk about red beds. Okay, I don't think we should be messing with that term in the year 2021. It's kind of obsolete. It's got to go. Then we're going to talk about, I'm going to give you a virtual tour of some classic red bed type mines. And unfortunately, all of these are pretty much in the US because I haven't been traveling much because of COVID over the past few years. So hopefully when I do this next time, I should have some examples from the Central African Copper Belt or maybe the Cougar Schiefer. And then the third part of the talk is, if I'm telling you not to use the term red bed, and if red beds are not a predictor of sediment-hosted copper, what should be used instead? Okay, what are some alternatives? So that is the plan. So we'll take a step back. Let's talk about copper in general. And for those of you who are not very familiar with where copper comes from, most of it does not come from sedimentary rocks. Actually, most of the world's copper is produced from what we call porphyry deposits. And then there is copper in volcanogenic massive sulfides and iron oxide copper gold deposits. Then there's copper skarns. So there are several other sources of copper, and those actually make up the majority of the world's copper production right now. So where does sediment-hosted copper, where does that come in? That is between, depending on who you talk to, it's anywhere between 23 to 25% of the world's total copper production right now. Now, the folks at the USGS, what they've done is they've split up sediment-hosted copper into 3 different categories based on what they think are models we can use to predict their occurrence. So what they've done is they've split them into 3 different parts. There's the reduced facies type, which most people would refer to as the Cougar Schiefer type. Okay, so this is copper that is being hosted in fine grain deposits. So essentially, classically, it should just be mud rocks, but as you'll see later on, it's not as simple. Okay, then of course there's Revette type copper, and that's a special case where the reductant for the copper is essentially hydrocarbons or hydrogen sulfide that's in the rocks. And then they split that up from what they call red bed type copper. Okay, and this is the one we're going to talk about most today. But hopefully after I'm done with the talk, you'll see that a lot of these lines are not as clear as they seem. Okay, now there's a lot of terminology when it comes to copper. Some people call it sediment-hosted copper. Some people like to call it stratiform copper. Some people like to call it strata-bound. Some people like to call it sediment-hosted stratiform copper. I mean, you know what? I'm not going to get into this discussion. If you're really interested, there's an entire paper that discusses nothing but terminology of what you should call it and why you shouldn't call it that and all that stuff. So we're not going to get into it. If you really, really want to know, let me know, and I'll send you the reference later on. Now, the grades in sediment-hosted copper, average grade is from 1.1 to about 5%. And if you throw in the Central African Copper Belt, these values can jump up to about 10% or so. But that's unusual for sediment-hosted copper to be that high grade. More typically, they're in the 2 to 4% range. The deposits aren't super thick. They're 30 meters. And more typically, they're less than 3 meters thick. So let's talk about the model. So the model's been around for quite some time, and there's quite a few people that have contributed to the model, and most recently it's been Murray Hitzman, and this is a cartoon out of one of his publications. And the general idea is that you need evaporites, and you have brines that are being sourced from the evaporites. And as those brines enter red beds, the red beds are the source for the copper. The brines will scavenge the copper out of the red beds, and then when those fluids start migrating, as soon as they encounter a reductant, you'll get copper deposition. So that is the classic model, and there, of course, there's a few variations on that model, but that is the general idea. So the mining industry is moving more towards what we call a mineral systems approach, which is very similar to the petroleum systems approach in the sense that you want to know what the source of the metal is, you want to know what fluids can mobilize it, and more specifically, you want to know what the pH levels are for that fluid, you want to know what the salinity is, what the temperature range should be. So all that stuff's important. And then finally, why do we get entrapment? What causes the metals to deposit out? So in this case, the source are the red beds. The fluids are sourced by evaporites. And then the entrapment is caused by the presence of reductants. So that's the red bed model in a nutshell. And we're going to look into that in a bit more detail. So why are red beds an important source for copper? There is a whole list. I've listed all the reactions. And of course, there's a ton of publications about all of these as to how you can possibly liberate copper from red beds. And you can see that there are certain minerals that are more commonly found in red beds, especially if you look at pyroxene and you look at how much copper is contained within that. You can notice that's up to 120 parts per million. So bottom line is red beds are an excellent source of copper. And what I don't want you to take away from this talk is that, Ali is dissing the idea that red beds are not a good copper source. No, I'm not doing that at all. In fact, I do believe that red beds can be a good source of copper amongst a lot of other things that are out there. Okay, so that's definitely not what we're doing here. What I'm saying is you shouldn't mess with the term red beds at all. Okay, why is that? Well, because it's a basket case term. What does that mean? Well, what that means is, let's assume you're out with a friend who just got back from overseas, and they're a paleontologist, and they told you that they just got back from digging up fossils in these red beds in Mongolia. So you're thinking, okay, red beds. Red bed means they're most likely working on Permian deposits. So you've already made an assumption. You made the assumption about the age of the deposits. And then they're like, okay, so they're digging up fossils from these red beds, and red beds are usually fluvial. Oh, that's another assumption. You just made an assumption that red beds are fluvial, and you were wrong on both accounts. Okay, so the red beds that a lot of these famous dinosaurs, like that famous fossil where the Velociraptor and Protoceratops are locked in combat. Well, those were Aeolian, and they're Cretaceous. So no, none of those assumptions worked. And we do that all the time. We're like, we go in, we see red beds, and boom, we start making assumptions already. And I'll tell you right now that just the color of these red beds, it's going to throw you off. It has absolutely no paleoclimatic connotation. Okay, so the first thing people assume, and of course this is what I was taught in school, is hey, when you see red beds, you're looking at terrestrial deposits, and they're most likely arid. And again, I'm telling you that's BS, which is bad science. Okay, so here's an example. This is a maroon formation here in Colorado. So let's look at some red beds, because I'll tell you, I'm originally from Pakistan, and when I was in high school, I started volunteering for the local museum, and I was just out there measuring a ton of stratigraphic sections when I was 15. In this series called the Shivalics, which is the thickest, most continuous fluvial succession in the world. It records sedimentation all the way from the Miocene to the Pleistocene. So this picture you're looking at, these are red beds in the Shivalics, northern Pakistan. Here's the Himalayas. This is where the picture is from. It's right between the Salt Range and the Himalayas. Salt Range is where all those Himalayan salt lamps come from. But anyways, you're looking at all these red beds, and I was confused. First SETSRED class, red beds indicate arid conditions. And I'm like, how is that even possible? Because all I remember is measuring sections and digging up fossil bones of crocodilians, turtles, and hippos. And none of those go with arid environments. So what's going on here? And of course, there's a lot of work that has been done on the paleosols of the shibboleths, mainly by Greg Rikalik and others. And this is a paleo-environmental reconstruction of what the shibboleths used to look like. And you can see that's anything but arid. And so folks have worked on this, and what they figured out is that, again, the color, the red color in the shibboleths is not an indicator of aridity at all. It's just the fact that it's got positive EH, neutral alkaline pH conditions. You've got a conversion of ferromagnesian hydroxides into ferric oxides, and that gives the red coloration. It is not an indicator of arid conditions. Well, the other thing I got taught in school, like many others, is like, hey, when you see the color red, that's oxidation. So if it's oxidation, that's an indicator of terrestrial conditions. And again, there's a lot of geoscientists out there who still hold on to that. And an example of that is from the Marat beds. These are in Kuwait. In Kuwait, they're producing from this in the subsurface. And for years, people saw these and they assumed, just because they're red in color, they assumed that these were terrestrial deposits, until more recently, the people have worked on some outcrops in Saudi Arabia. And what you're looking at here are tempestites. That's hummocky cross stratification and swaley cross stratification. And so, you're in marine conditions, yet everything is super red. Again, so you can use red beds as an indicator of terrestrial deposition. So this term is so darn shaky that if this is what you're going to hang your hat on, if this is your exploration model, is, okay, we're going to go look for these red beds, and where we're going to find the red beds, we're going to find sediment-hosted copper. Well, man, you know what? That's a bad start right there. Okay, so let's look at some classic red bed deposits on the Colorado Plateau. And what I want you to get out of this is the diversity in environments of deposition where the copper occurs, so the host rocks. And I want you to think about the reductants, the diversity in reductant types. Okay, so some of these are actually red, most of them are not, but whether they're red or not, they've all been put in this classic red bed model. So these are the places we're going to go look at. The numbers correspond to different mining districts. So what we're going to do is we're going to start here in Utah, and we're looking at the Big Indian Mine, 150,000 tons at 1.5% copper. And what you're looking at is a redox cline. Okay, so you can see there's a very sharp color change right there. Everything on the left is red, which is oxidized. Everything that is not red is reduced. Well, why is it so sharp? Well, it could be a few different reasons. It could be that, oxidizing fluids started going through, rocks with a lot of reductant in them until they finally reached a threshold, and that's where that happened. That's one possibility. Another possibility is that there's a fault there, and there's fluids that are coming up from the fault that are reducing. Okay, so there's multiple reasons for why that redox cline is so darn sharp. But that redox cline occurs throughout this area, not just in mudstones, but in sandstones as well. So in this picture, the sandstone you see back here is the exact same sandstone right here. It's a channel, but you can see the color difference. Okay, this right here is the exact same as that sandstone, except that we're looking at, it's crossed a redox cline. So on this side, it's reduced, which is why you can see the green in there. Okay, copper needs to meet reductants for it to precipitate, and that's what's going on here. Okay, so the green is malachite, and there's absolutely no copper in the oxidized stuff back there. Okay, so the source, most people assume they're Permian red beds. Now the word, again, you're going to hear this word assume a lot, and I think in the year 2021 we have to stop assuming and start testing. Okay, so the assumption is that the source is the Permian Cutler group underneath. The transportation occurs when we've got paradox salt underneath. So halite and carnallite derived chloride-rich brines are moving up through the rock column, and they scavenge the copper out of the Cutler, and they deposit it in the Burrow Canyon Formation, which is what you're seeing here. Okay, and the trap in this case happens to be a redox cline. So what we see at Big Indian, we saw that the reductant was basically organics, and to be more specific as to what organic they are, they're essentially a whole bunch of wood chips. Okay, that's what we're finding at the Big Indian mine. A lot of the copper is actually in these small wood chips and disseminated organics. And it's in a fluvial environment, subhumid. A lot of those channels are part of small lacustrine deltas. So let's talk about something very different. Okay, this is not too far off. This is the Cashin mine. This has produced a lot, around 11 million tons, but at a lower grade. Like almost 0.43% copper. And same sort of source, Permian red beds, and transportation is by the paradox brines coming off of the paradox salt. But what's going on here? Well, again, you're looking at a whole bunch of malachite in green. The blue is azurite, and most of the ore is disseminated. So what the reductant? Well, the reductant in this case is bitumen. Okay, so at some point, hydrocarbons migrated through the Entrada, the Wingate sandstone at this particular location, and that bitumen is providing the reductant for when copper-rich fluids were migrating through, and that's why you got copper precipitation. That's one way of doing it, and that's been described in the literature. That's the classic model. The not-so-classic model is the presence of microbial carbonates in the inner dunes. Okay, and here's an example. So here you've got some microbial carbonates right here, and you can see that there's a lot of green in there. Well, why is there a lot of green in there? Well, again, that's because these microbial carbonates are very organic rich, and they're providing the reductant. So same mine, two very different types of reductants. Here's another mine, different formation, different mechanism. Okay, so this one happens to be in the Chinle, and what's happening here is you're looking at the base of a channel, you're looking at the lag at the channel, and what it's done is it's picked up bits of organics from the floodplain fines that it was incising through, and when copper-rich fluids migrated through, all that copper got precipitated right at the lag, right there. So it's associated with these fluvial channels in a subhumid setting in the Chinle. Here's another one. This isn't quite a copper mine. It's actually a uranium mine, but copper is a secondary commodity. So the light blue you're seeing is chrysocolla. Then the dark blue is azurite. There's a little bit of malachite in here too. Same sort of trapping mechanism in the sense that you've got reductants in the form of organic clasts right at the base of the channel, but it's a different formation. So still fluvial. This time it's not quite humid. It's not quite as sinuous. Very different, slightly different depositional system. And this time it's on the Morrison Formation, not the Chinle. So if you looked at all of these together, what's going on? Okay, so sources of copper, like I said, people have assumed they're the red beds. No one's really been able to test that. The transport we understand pretty well. They're being mobilized by brines sourced by the paradox salt. So if you look at these mining districts, I showed you the Copper King mine, that's from Moab Valley. I showed you Big Indian mine, that's from Lisbon Valley. And then I showed you the Cashin, which is right next to the Paradox Valley. Well, what do all three of these have in common? Well, the valleys are there because these used to be salt walls. Okay, so the salt has dissolved, and the valleys are what are left behind. So all three of them have in common are large diapiric salt bodies. So let's move further south. Let's go to New Mexico. Again, very different environmental deposition. This time we're looking at the Grayburg Formation. And if you're looking at the Grayburg, the environmental deposition we're looking at right here, that's a Safka setting. And these veins that you're looking at, that is sand and spar gypsum, okay? So very different mechanism of entrapment here. So what is the source? Again, people assume they're Permian red beds. Again, that's an assumption. It hasn't been tested. What is the transport mechanism? Well, in this case, you've got a lot of halite in the San Andres Formation. So fluids that are coming off of that are providing the chloride-rich brines that we need to mobilize copper. The host rock in this case happen to be tidal channel sandstones in a coastal Stauber setting. What is the trapping mechanism? It's actually bacterial sulfate reduction of gypsum. So there's a lot of gypsum in the middle in this formation. There's bacteria that feed on the sulfur in that gypsum. They give off hydrogen sulfide, and it's the hydrogen sulfide which provides the reductant for copper deposition. Now, very close to the last mine, which was Pintada, is the Stauber Mine in New Mexico. And this time, again, very different formation. Again, the source is believed to be Triassic red beds in this case. The transport is the same. The host rock is very different. We're no longer in the Stauber. We're in a subhumid climate. And what is the trap? The trap is actually a log jam. So these fluids oxidize, these fluids were mobilizing copper. They keep going through this log jam until they finally reach a threshold. And there's a redox cline right there. And on one side, everything is oxidized. And you can see all the logs are iron permineralized. And once you cross that redox cline, and again, very, very sharp contact there, all the logs are chalcocite permineralized. Okay, so they're copper permineralized on the other side of the redox line. And of course, the copper is all in the redox, is all in the reduced facies. So what about these two mines? What do they have in common? Well, if you look at them, here's the town of Santa Rosa, right on the old Route 66, and you see a bunch of these round lakes here. Okay, and you will look at this, you're like, oh, that's karstification. And it's similar. The process is similar in the sense that these are caused by evaporite dissolution. Okay, so right here we have, again, what it tells you that we had a lot of San Andres salt, which is evacuated, and that's what these two mines have in common. So we're going to run through a few more before we wrap this thing up. So this is Nacimiento, New Mexico, hosted in fluvial deposits. What's the reductant? Again, another log jam. Okay, lots and lots of wood that you see here. It's black because it's been permineralized by chalcocite, and then the greens you see are malachite. Here's a slight twist on the same theme. In this case, someone has actually studied the source of copper, and they figured out that even though this formation is completely red, it is not arid. In fact, you find tons of fern fossils in there, lots of calamites as well. And the source are actually volcanics and not the red beds themselves. Host rocks are fluvial channels. What is the trapping mechanism? The trapping mechanism are actually paleosol horizons. So what you're looking at right here are root traces. So these root traces will go on for several hundred meters, and they're copper permineralized. Okay, same thing in the Warnock Mine, New Mexico. Again, if you look at these in map view, what do they have in common? Well, here's a diapir that's almost made it to the surface. There's a whole bunch of mines they're mining potash out there from the San Andres. So again, what do they have in common? There's an evaporite diapir very close by. Now, the last time I gave this talk, it was for the Denver Mining Club, and I showed this, and of course, everyone out there are folks that have worked their entire career in the mining industry. And of course, the first thing they check for is the grade and the tonnage. And they're looking at this and they're like, hey, you know what? You showed us a ton of examples from tiny deposits. Okay, so how does this apply to the bigger systems? So, we're going to look at the two largest systems in the world. We're going to look at the Kupferschiefer in Europe. And back in the day, they had a super simplistic model of the Kupferschiefer, which was, we've got red beds underneath, brines move through the Kupferschiefer, through the red beds, they collect all the copper, they hit the actual Kupferschiefer shale, and that's where you get copper precipitation. So it's right on that shale. But recent work done mainly by Gregor Borg shows you that, you know what, the copper is all over the place. Sometimes it's in the red beds themselves, sometimes it's in the shale, sometimes it's actually above the shale. So it can be all over the place, and that's because the redox cline has moved through time. Okay, so it's not as simple. There's a lot more detail that goes with it. Here's the Bahama Mama of copper deposits. This is the Central African Copper Belt. And in the Central African Copper Belt, again, what I should have pointed out in the Kupferschiefer is no matter where the copper happens to be, what all of them have in common is this Zechstein evaporite. You look at the Central African Copper Belt, and if you're looking at a map right here, all of these things are salt mini basins, okay, that were formed before the copper was being deposited, and a lot of that evaporite has actually dissolved. A lot of diversity when it comes to reductants. If you're in Zambia, a lot of that reductant is actually pyrite. And if you moved into the DRC, and if you look at some of the recent discoveries like Kamoa and Kikula, those discoveries are associated with these siltstones and glacial diamictites, but again, very, very different sources of reductants, including microbial carbonates. So this was the last publication on the topic. This is again by Murray Hitzman. It was in the 100th anniversary edition of SEG on mineral deposits, which is like the Bible for every mining person out there. And if you look at this, of course, these are the three options they're giving you. It's like red beds plus evaporites, red beds with overlying evaporites, red beds with underlying evaporites. The evaporite part, I agree with 100%. The problem I have is with the red beds. This sort of reminds me of when Exxon first came out with the global sea level curve, and people were going crazy because they're like, oh my God, I've created a sea level curve based on my seismic data, and it matches perfectly with Exxon's global sea level curve. So this must be magic, until Andy Mile came out with this idea that you could scribble a curve no matter how, and it would still have at least a 60% match with the Exxon sea level curve. So red beds are sort of the same way, in the sense that no matter what, if you start thinking about any basin that you have ever worked, and you're super familiar with how the basin works and the stratigraphy, man, there's going to be at least one or two intervals in there with rocks that are red in color. And if you're going to call every rock that's red a red bed, well, guess what? Yeah, of course the model is going to work, because they're everywhere. Okay, so what I would recommend is, we don't do that, because that's a bit silly. You can't just call anything that's red colored a red bed and then assume it's going to be a source of copper. Evaporites are an excellent predictor, especially large evaporitic bodies. Those are excellent predictor. And why are they a better, more useful indicator than red beds? Well, because guess what? In most of the world's large basins where we have large salt diapirs, we've got excellent seismic data. Okay, we know where the diapirs are. We know, we can, on seismic, we can actually see migration pathways. So if there's a diapir right here. So I feel like there's a lot of data that is out there that could be used to explore for sediment-hosted copper deposits, giant sediment-hosted copper deposits. And then you don't have to categorize these things as to being, oh, this is the reduced facies / Kupferschiefer type, oh, this is the red bed type, oh, this is the revet type, because all of them have one thing in common, and that is the presence of large bodies of evaporites. So if I were to teach a course, in a place like the School of Mines, and I was teaching folks how to go look for sediment-hosted copper deposits, I think the first place to start would be to look for basins that have large volumes of evaporites. And I keep saying evaporites because that's in the literature. I should be more specific when it comes to that too. Not all evaporites are the same. So you could have a bunch of anhydrite and gypsum, and they're not going to liberate the chloride-rich brines that we need to mobilize copper. So it's just not going to get mobilized. So when I say evaporite, we need large bodies of evaporites. I should be more specific and say that we need a lot of halite or carnallite or something else that can source chloride-rich brines. The other thing is reductants are highly diverse, and it is the one thing we have learned after exploring for sediment-hosted copper for over 100 years, is that the distribution of copper at a district scale is actually where the reductant is at. So I think the key here is to be able to predict the distribution of reductant in a basin if you want to figure out where the highest grades of copper are going to be. Again, I'm definitely not arguing that red beds can be a good source of copper. I think they can, but again, you have to remember they've got zero paleoenvironmental connotation. They can occur in a lot of different environments of deposition, and not all of them are going to be sources of copper. We shouldn't assume all evaporites are the same. Some evaporites are great for copper mobility, like I said, such as halite, carnallite, sylvite, etc., whereas others can provide a reductant, for example, anhydrite or gypsum because of BSR, which is bacterial sulfate reduction. And finally, this is something I say after pretty much every sediment-hosted metal talk that I give, which is if you're going to be working on these systems, man, you got to put some sedimentology back into sediment-hosted exploration, because if you're not going to do that, if you approach these like porphyries or VMS deposits, it's just not going to work. It's just not going to be a solid model. So that's all I have for you guys today. If you have any questions, I'll take those at this point.